Hello everyone, my name is Zhang Shuhan, and now I will introduce the method that I use to solve the question 2 on homework 10. In question 2, we need to write the proper definitions and properties of stochastic process. First is Whiteside stationary process, and second is independent increment process, and third is Markov process. The fourth is normal process, and the fifth is strict stationary process, and sixth is white noise, and seventh is mean ergodic processes, and number 8 is martingales. And first, we need to write the definitions of Whiteside stationary. In Whiteside stationary, the means of a constant, the means is constant, and the autocorrelation is a function of time difference. Furthermore, the WSS only use mean and autocorrelation in practice. They are much easier to get second order density based on mean and autocorrelation functions. We can do many things already. We can do state estimation and parameter estimation and prediction in mean square sense. In communication application, in most cases, we do not care too much on specific value of stochastic process. We pay our concentrations on the power of signal. The autocorrelation functions are T1, T2. If T1 equals to T1, if T1 equals to T2, RT1 T1, RT1 T2 can be written as RT1 T1 is the average power of signal at T1. We see that when the input is WSS process, the output of stable and linear time invariant system is also WSS. The second, we will discuss the independent increment process. Means big X1 minus X2 and X3 minus X4 are non-overlapping intervals. If the intervals T1, T2, and T3, T4 are not overlapping, so the increment process are independent. So we can see that Poisson process, random walk, and Wiener process are independent increment process. It means independent increment property is somehow relative to Markov process. And now we are going to discuss the Markov process. And the Markov process has a property that the past has no influence on the future when the present is known. And we now going to discuss a little bit. We see that Poisson process, Poisson impulses, and semi-random telegraph, random walk, and Wiener process are all Markov processes. In the real world, many processes have Markov property. And so next, we are going to discuss a normal process, which is also called Gaussian. A process big xt is said to be normal if the random variable xt1, xt2, to xtn are jointly normal for any n and any t1 to tn. And we can write this probability dense functions like this. And vector small x is a matrix, is a column matrix of x1 to xm. And vector big X denote the matrix, denote a column matrix of big X T1 to big X Tn. And eta is the expectation of big X, and C, which is covariance equals to the expectation of big X minus eta times the big X minus eta transpose. Discussion. The statistics of a normal process is completely determined in terms of its mean eta t and autocorrelation RT1 T2. In general, eta t is a function of t. In this course, we classified Wiener process as one example of stochastic processes, and we classified normal processes as a property of stochastic processes. This is, we treat normal process as a larger class of stochastic processes and treat Wiener processes as specific examples. Next, we are going to talk about the strict sense stationary processes. It has a property that the statistic is not affected by a sheet of time axis. So we can see that the SSS processes requires big fs x from x1 to xn, t1 from t1 to tn equals to fx x1 to xn and t1 plus epsilon to tn plus epsilon. The conditions is very hard to meet. So the next we are going to talk about white noise. For the Wiener process Wt, if we wish to discuss its derivative Vt, which is dWt divided dt, we have the excitation of Vt equals to 0, and autocorrelation of V equals to alpha times delta T1 minus T2. Wiener process does have derivative. We use Vt to denote it. When we need to further discussion, instead of big Vt times dt, we use dWt. Wt is continuous with probability 1. It has differential dWt. Vt equals to dWt divided dt is Gaussian white noise with zero means and impulse autocorrelation functions. We wish to define more general white noise with zero mean and impulse correlation function. A stochastic process big Vt is said to be white noise if the expectation of big Vt equals 0 and the autocorrelation of Vt at T1, T2 equals to Qt1 times delta T1 minus T2, which is impulse autocorrelation function. And the number 7, we are going to talk about stochastic process big Xt is said to be mean ergodic process if we have limit t equals to infinite and the 1 over 2t and times the integral from minus t to t, the big Xt equals to the excitation of big Xt in mean square sense. And in mean square sense, it's not kind of consistent array. There are others in probability with probability 1. In other course, we discuss in mean square sense only. A stochastic process big Xt is said to be martingale if the excitation of Xt under the condition of big Xs equals to x1 should equals to small x1, where s is smaller than t. The condition means equals the condition. The conditional means equals the condition. This is true for random walk and Wiener process. That's all. Thank you.